Okay, after knowing what is entropy and its properties, let's find out what is the entropy change for a reaction. Entropy increases in three situations. When a reaction is a decomposition reaction, when one molecule changes to more than one molecule. So when we have A changing to B plus C, two molecules have more entropy than one. A reaction where you have increase in number of gas moles, gas molecules. A good example is when ammonia, 2 moles of ammonia change to H2 and 2 plus 3H2. All of them are gas. So how many moles of gas you have on the left side? 2. But you have 4 moles of gas on the right side. And you know gases have the highest entropy because they can move fast in random directions in normal temperature, of course. So that's the second situation. The third situation is when a solid changes to liquid or liquid changes to gas. Example would be when calcium carbonate solid changes to calcium oxide solid plus carbon dioxide gas. So you have no gas molecules, and solids, you know, solids entropies are almost zero. And again, you have another solid, but you have 1 mole of gas on the right side. So this is going to change the entropy of the system. Another example on slide number 51. When you are working on barium hydroxide 8H2, do you remember what would you name these types of compounds? Ionic compound, which is loosely attached to some water molecules. You remember we called them hydrates, right? It's not the discussion here, but just a quick reminder. Plus 2 NH4NO3, 2 moles of ammonium nitrate. They are both solid. They change to 2 NH3 gas plus 10 H2O liquid plus BaNO3 2, and this is aqueous. The question is asking, it describes this exothermic reaction of solid barium hydroxide octahydrate and solid ammonium nitrate. They react with each other. You're supposed to predict the sign for delta S. Let's introduce this equation here. This equation needs to be memorized. It's not going to be given in the exam. To be memorized. This is in a form of mathematical equation, but it's more conceptual. So delta S is the summation of entropy formation or entropy standard of the products, considering their coefficients, minus solve reactants. So, going back to our example, we have 3 moles of reactants on the left side And how many moles on the right side? 2 plus 10, 12 plus 1, 13. So if we just go, instead of S, go by number of moles, we have more number of moles on the right side. And also you can say that here you just have solid, but you have gas and liquid and aqueous. Which one has more disorder? Which one has more movement? Of course the right side. So delta S for such a reaction is going to be positive. Delta S standard is going to be positive. So let's work on another example where we are utilizing this formula. In the previous formula, in this formula, we just worked with the states. But here we are going to work, in the next example, going to work with this formula. Let's go to slide number 53. An equation of ethanol, CH3, CH2OH liquid, burned in oxygen to form carbon dioxide, no, it's oxidized to acetic acid and water. Okay. The standard entropies of the substances are given. For the liquid ethanol, it's 161 joules per Kelvin mole. For oxygen is 205 joules per Kelvin mole. For acetic acid is 160. And for water is 69.9 joules per Kelvin mole. What did we say? Delta S is the sum of entropy of products minus the reactants. So delta S standard, all the coefficients are 1. So for the products is 160 plus 69.9 joules per Kelvin mole minus 161 plus 205 joules per Kelvin mole, which is going to give you minus 135 joule per Kelvin. So you already multiplied by the mole, so it's going to be Kelvin only. Kelvin in Kelvin. You might say, why are you wiping out the mole? Because we have multiplied by 1 here and 1 here. These are the number of moles. So mole and mole are cancelled. Okay, that's how you determine the delta S for a reaction. The next concept that I promised you that we will work on it in the previous video is actually the last term, the last quantity that we will work on in this chapter, which is called free energy. Free energy, which is shown in G. G stands for Gibbs, because a physicist, Willard Gibbs, he introduced it. It's called free energy. It's a thermodynamic quantity. We define it as G is H minus T S. Don't worry about how they got it and the rest of the story. what you need to know is that delta G standard is delta H standard minus T delta S standard. This formula will be given in the exam, but you need to know how to work on it. So a question about it will be slide number 57. I wish I had erased that slide. It's about, again, the same methanol, liquid methanol, which burns in oxygen gas to form acetic acid and water. Let's see what question is asking. Using standard enthalpies of formation, delta H formations, which will be given if you need to work on them, and delta S values, delta S standard values from the previous problem. Calculate delta G standard for this reaction. So delta H standard formations for ethanol is minus 277. Minus 277.6. Again, they will be given in the exam. Kilojoule. For oxygen, delta H standard is 0 because for the elements in their most stable state, delta H, you remember from Chem 1 is 0. For acetic acid is minus 487 kilojoules. And for liquid water is minus 285.8 kilojoule. So if you want to find the delta H formation, you remember delta H standard is, again, products plus minus is minus, right? Minus, I hope it doesn't confuse you, minus 277.6 plus 0. So delta H standard is going to come up as 495.2 kilojoules. Delta S standard, we found it from last problem. It turned out to be minus 136 joules per Kelvin. Delta S standard was minus 136 joules per Kelvin, and temperature is 298 Kelvin, right? So be careful. Delta S, you can change delta H to, it's in kilojoules, you can change it to joules, or for delta S, it's in joules, you can change it to kilojoules. The norm is we normally report them in kilojoules, so let's change it to kilojoules divided by 1,000, so it's going to be minus 0.136 kilojoules per Kelvin. Okay, so now you can say delta from this formula, delta G standard is delta H is 495.2 kilojoules minus T is 298 times minus 0.136 kilojoules per Kelvin, and this is Kelvin also. So delta G standard after this calculation, it turns out to be 454.7 kilojoules. So now you know delta G is negative, when delta G is less than 100 is spontaneous. We work on the criteria for delta G. And delta G standards are given. If you need them, you will have them later on. Just just like delta H and delta S. Delta G is also a state function, and how to find delta G standard for a reaction is the same exact N, the number of moles or coefficients, times delta G standard of products, minus N delta G standard of reactants. Alright, so now you have an example on slide 64. The same exact reaction plus O2 gas gives CH3 COOH, which was liquid, plus liquid water. Delta G standards are given for each one minus 174.8 kilojoule per mole. For oxygen is 0. For acetic acid is minus 392.5 kilojoule per mole. And for water is minus 237.2 kilojoule per mole. So plug it into this equation. Delta G standard is 1 times minus 392.5 minus 1 times, or let's say plus, include minus here. Moles are multiplied, so it's just kilojoules, minus the right side, 1 times minus 174.8, and it's going to be kilojoules. So delta G standard is going to be minus 454.9 kilojoules. You see, the same thing you found in the previous example. The criterion for spontaneity based on delta G. So we said we cannot decide on the spontaneity of the reactions based on delta H, but based on delta S and delta G we can talk about spontaneity. Basically, when delta G standard is less than minus 10 kilojoules, so it's called a spontaneous. When delta G is small, minus 10, less than minus 10 kilojoules. When delta G standard is more than positive 10 kilojoules, then it's going to be non-spontaneous. And when delta G is between minus 10 kilojoules and positive 10 kilojoules, basically very small or 0, not close to any of them, or almost 0, then a system is at equilibrium. So if you have the value for delta G, you can easily decide on the spontaneity of the reaction. Okay. Moving towards concept check on slide number 67, consider this reaction: N2 gas plus O2 gas gives 2NO gas. From the standard free energy of formation of NO, which we find it from literature, from your book or internet, is 173.20 kilojoules. We are supposed to find what can we say about this reaction as far as the spontaneity, of course. Delta G standard for this reaction is 173.20, and you see you have 2 moles of NO. It's supposed to be per mole, so you divide it by 2, and delta G standard is going to be 86.60 kilojoules per mole. Again, because you have 2 moles of NO, 2 moles of NO as formed, and you need to have delta G standard for 1 mole. So this reaction, what is the measure? Is it less than 10 kilojoules or more than 10 kilojoules? It's more than positive 10 kilojoules. So it's a non-spontaneous reaction based on what we just said, the criterion for the. So you can predict which one is which reaction is spontaneous, which one is non-spontaneous. So if you call this, if you have a graph of free energy, delta G standard, based on, you call it reactants, and here you will have the products. If delta G, we said products minus reactants, right? If delta G less minus more is going to be negative, of course this is delta G standard between the product and the reactant. So you have a spontaneous reaction. Free energy decreases. Like for gasoline and oxygen in your gas tank, and forming carbon dioxide and water. So this is going to be the spontaneous reaction, and at the end, system reaches to some sort of equilibrium. We said spontaneous reactions occur by themselves and continue until they reach to an equilibrium. But a non-spontaneous reaction, this was a spontaneous. We have a little bit already. If we have delta G, then for a non-spontaneous, if you have the reactants on this side, products on this side, you remember the rolling the ball uphill, you need to push it. And this is going to be again delta G standard, and it's a non-spontaneous reaction because delta G, which is G of products minus reactants, is higher minus lower, but delta G is going to be positive. So this is another sign. If a diagram is given and asking for spontaneous or non-spontaneous, you can decide. If it's going downhill, it's spontaneous. If it's going uphill, it's going to be non-spontaneous. All right, the last thing about delta G is that, and you will need it for the next chapter also, when you learn about cells and electrochemistry, is how to interpret the free energy. Spontaneous reactions, we can use them to perform work, just like when we put gasoline for our vehicles to work, to move a vehicle. Then we can get the maximum work of the system from delta G. So you can say delta G is the maximum work that a system can do. Now let's relate this delta G to the equilibrium constant. Yeah, and you remember when you had just gaseous compounds, K equilibrium, we call it Kp, right? And when we had the solutions, K equilibrium was Kc, right? So, like for example, you have examples, I mean, when you have N2O4 changes to N2NO2, then K for this is going to be Kp, right? Because both of them are gases. So it's pressure of NO2 squared divided by pressure of N2O4. You have all of these. I don't have to mention it again, but just a quick review. And the second one, if you have solid zinc plus 2 hydrogen in an aqueous solution. And if you have zinc ion plus hydrogen gas, so how to write the K equilibrium? K equilibrium is going to be, you have an aqueous zinc, so it's going to be solution, so you need the molar concentration. Hydrogen is gas, so you can say P of hydrogen, divided by, solids are not included in the equilibrium constants, and then you have an aqueous hydrogen, which is to the power of its coefficient. All right, and the relation between the delta G, energy, gives free energy, and equilibrium constant, and again you will use it in the next chapter, is going to be delta G is delta G standard in the standard conditions plus RT, L, and K. We are not worried about how to find these formulas because these formulas are always given. If you have equilibrium, if the system is at equilibrium, what did we say about delta G? Delta G is going to be 0, right? Almost 0. So if you put it here, delta G standard is going to be minus RT, L, and K. Okay? So, or let's say, we say at every moment of the equilibrium, of the reaction, delta G is delta G standard, whatever we have a standard for it, plus RT, L, and Q. And then at equilibrium, because delta G is 0 and Q at equilibrium is K, right? You remember we said K and Q are the same. The difference is that K is for equilibrium and Q is not for equilibrium. Then you can have delta G standard is minus RT, L, and Q. This is a very important formula which will be given again. So you can work on different examples you have. Calculate the value. We're working on slide number 74. Calculate the value of the thermodynamical equilibrium constant for this N2O4 gas gives 2NO2 gas. The standard free energy of formation is 51.30, 51.30 kilojoules per mole for NO2, and for N2O4 is 97.82 kilojoules per mole. So we can calculate delta G standard first. Delta G standard is 2 moles times 51.30, which is kilojoule, minus 1 times 97.82. Again, just gives you kilojoule, which is going to be delta G standard is going to be 4.78 kilojoules. What are we supposed to find here? Calculate the value of a thermodynamic equilibrium constant. So we have delta G standard now. 4.78 is minus RTLNQ, which is 8.315. We're talking about joules, so it's joule per mole Kelvin. T temperature was how much? 298 Kelvin. And you have your unknown L and K. So you find L and K by dividing this side by this side, and then K is going to be 0.145 by using this. So if delta G standard is not given, you can calculate it from delta G standard formations. But don't forget, these are delta G standard formations. But if this delta G standard is already given, just plug and chalk in the equation. And the very last the very last example is the example that you have everything. Yeah, it's based on the formula that you had before. I'm sure you know how to work on it. Just don't want to take the time of the video just because of the formula that you know already. T is delta H standard over the delta S standard, or let's say you had delta H is T delta S standard, because the question says it's just working at temperature that reaction proceeds spontaneously at 1 atmosphere. So you don't have to be worried about delta G. Alright, you have a lot to do and work on. Feel free to ask your questions.